Welcome everyone for a new energy system seminar. And today we have Paolo from our department who will present his research on economic evaluation of transition pathways for Norway, insights from the REMES-Norway CGE model. And Paolo is a researcher at the Industrial Economics and Technology Department. And he finished his PhD some years ago, many years ago, and he is now involved in multiple energy-related research projects. So please, the floor is yours.
Good. So I'm gonna show a little bit what I'm working on, what I've been working on. This is some work that is related. So first of all, my main activity here is microeconomic evaluation of decarbonization pathways. So this is mostly what I do. And I'm using a macroeconomic model that is called REMES, and it's a computable general equilibrium model. So it's not based on, for example, econometrics, as many of you might know about econometrics, but it's based on equilibrium. It's based on microeconomic theory and equilibrium between the different parts in the microeconomic system, in the macroeconomic system. So it's like having a macroeconomic model which is founded on microeconomic premises. Okay? So that's how it works. And we applied this REMES model. Both, we have two versions. We have a European version of the REMES, and we have a Norwegian version of the REMES. European version has been applied in three European projects so far. And it's used mostly for decarbonization analysis for European transition. And the Norwegian one has been applied to two Norwegian projects by me. I think it has been applied also in other projects by people in SINTEF, because this model has been defined initially by people at SINTEF together with NTNU. Now I'm maintaining it for NTNU, and I'm building upon the first version of it and including new features. Okay, so here I'm going to show an example. After introducing it, a little bit what I work on, what are the tools I use, I'm going to explain a little bit how this has been used in the NTRANS scenarios for evaluating the NTRANS scenario. NTRANS is a center, you know about it. So, and there are many sort of research areas that are considered. It's mostly related to energy and decarbonization, right? So here we've been creating pathways. We've been devising pathways for the decarbonization of Norway. And these pathways that are initially just storylines, verbally written, were turned into numbers quantified for different models. One of them was REMES. Okay, a little bit about what I do. So I start normally having storylines about future technology, policy, and societal structure, about a country, for example. So storylines are text. What's going to happen? I quantify this. All people do quantification here. After the quantification of the pathways, there is a quantification of the scenarios through the model. And this quantification of scenarios, basically running the model, what it gives us is normally, we have GDP sort of projections of what could be the impact of some policies, some technology change, and so on, some change in behavioral pattern. Information about welfare would be, for example, the cost of living related, welfare related, or for example, it could be gender gap, something related to welfare aspects. Sectoral output, we have how much each different sectors increase or decrease their activity depending on these policies. Demand and supply, and also prices for different commodities. And emissions. This is mostly what we get out of this model. After that, normally I run a sensitivity analysis, trying to see if this, to check how each of the single, because normally I model an entire sort of scenario, a lot of shocks. I run a shock at a time just to see which shock gives a given effect to the system. Okay. So I use general equilibrium models. What are general equilibrium models? They are a class of economic models that use actual data, normally a table with the flows of money from each agent, each sector to each sector, to compute what could be the impact in terms of changes in policy, technology, or other external factors. They consider multiple sectors, all the sectors in the economy, possibly. They consider the whole economy, in fact. And we just consider agents as price takers. So everything is considered as to be, for simplification, perfect competition within the sectors. So prices are the only role of the prices. They are not considered strategically. They are not defined strategically by different sectors, but they just change to ensure that demand is equal to supply for each commodity. That's what they do. They are applied, and again, they're based, these I can just skip. They simulate the behavior of the modeled economy as a response to a shock. So the shock will be policy. I make a law that prevents the extraction of gas by 10% for the next 5 years, every year going down. It's a law. This is a shock. Or I include a tax on the consumption of some types of food, like meat.
Goals for Norway. They also included like climate goals for Norway. Like
so there are also climate goals. One of the shocks could be, for example, to reduce CO2. How much we are emitting in total, and then we reduce it. Of course, this is normally related to a price. It's a macroeconomic model. You can't just say that. In some cases, when you reduce a resource, there will be a price connected to this resource. If you have to buy it, for example, that will reduce the demand for it. In some cases, you just reduce the amount available of a resource, which will increase the price in this case as well. Okay, so out of that, we provide information for prices, demand, supply. I already said that about GDP, and could be also unemployment, could be one of the variables in the model. So how is it structured? We consider a group of actors. So actors could be final consumption, typically. So households are an actor, government is another actor, investors is another actor. They buy things, or either for consumption or for investment or as public expenditure. And also we have different sectors. So each sector maximizes the profits, and each actor maximizes the utility function. These actors are equipped with the utility function. They try to maximize. I assume that everybody is familiar with the concept of utility function. Okay. So, and at the base of the whole system, we have the availability of resources. So how much labor do we have? How much labor force do we have? How much oil is in the economy available for extraction? How much capital ton? What is the emission budget for this year? Let's say it's going down. This will change the impact. And also these models are in a way simplified because they put together different sectors and different commodities. We don't talk about, let's say, Dals beer, but we talk about beer in general or food in general. So everything is very much bundled together. So we have to define different prices at different stages of the of where this product is. Here is an example. It's like a bird's eye view of how this sort of model look. So basically, here it's saying that we have a supply side and a demand side for one given commodity. And when I say one given commodity, I talk about, let's say, beer. But I'm talking about not Dals, not Ringnes. I'm talking about beer in general. It could be also Italian. So when we have this commodity here, it's like we need capital, labor, energy, and materials as inputs to every sector, to the sector producing beer in this case, for producing the domestic production. Domestic production will have a price called domestic production price. This domestic production is mixed with imports to create another, it's called variety of this product. And this is to simplify because we just have one product. But then when we mix it, Dals with Peroni, it's another type of, we don't mix it physically, but we're buying so many different types of beer that at the end we have a different variety of this beer, which will have a different price for the model because we are buying different types of. So when we import, we simplify by saying, okay, we have another variety and we have another price for it. Okay, then we have the domestic demand. Then domestic production on its own, which is mixed together with this. It's split between the variety that goes as domestic and the variety that goes for exports. So at every stage, this product is this commodity is either mixed, creating another variety, or split, creating two different varieties with different prices. They can change it. So it's like having different commodities. And the reason is that we are mixing or splitting things. Okay, the final demand, the domestic demand, sorry, is used, and the domestic demand is, again, if we are buying this mixture of import and domestic production, is used for final consumption, intermediate consumption, sorry, intermediary, it's intermediates there, and for investments. It could be, and it could be final consumption could be for households, or it could be for government. Like government, of course, is buying services mostly, right? They're buying like teaching services, for example.
For example, is there any type of restriction, for example, in materials, like the access to different type of materials that would become more scarce in the future?
It's possible to include it, not necessarily, but it's possible to include as a resource. There is a, for example, you can put a cap on the amount of lithium that's going down, because maybe China takes it all, and we're left without. Thank you. So, but yeah, so you can change it, and depending on the different countries, and then you have different prices for this this resource. Okay, I need to go on. So why is CGE? It's called CGE because it's computable. It's solved numerically. It's a big nonlinear system at the end. It's general because it considers the whole economy. And it's equilibrium because for every commodity we have supply equal demand, and we have a price that leads the supply to be equal to demand. The main components, we have economic actors. It could be consumers, could be production sectors. So also exports and traders are considered sort of sectors. There is this one sector in the model is one entity capable of having an input of different goods and having an output of different goods. Like, for example, in this case, the exports have the input, it's the production, in domestic production is the input for exports, and the output is the domestic production staying in the country and the domestic production going abroad. So exports is like a sector, and it works with utility functions. Utility function for putting input into one activity level, and sort of, let's call it production function, revenue function, for defining how this activity level transforms into output. Okay. So, and we have commodities and resources that are defined by prices and supply and demand for each of them. Consumers might be single households or multi-households. Very often we just have one household as consumer, and that defines the whole economy, all of us together, what we buy, how much we buy of this or the other, how much energy, how much electricity, how much, and we have data for this from the accounts, from the national accounts. How much electricity in terms of norske kroner has been purchased in year 2018? We have that. So we have, it's called supply use table. It's called actually, supply use table that you can find in SSB, in the Statistical Bureau. Right? So we have information about how much us as a single household, all of us, have purchased of each commodity. And that we say, okay, we have one representative agent with a given utility function that is calibrated to this data so that mimics, in a way, the behavior of the whole population. And then we have production sectors that employ capital, labor, energy, materials to create production, and they want to maximize the profits. Okay. How the data input looks like? It's something like this. I mean, this is a mock-up of how it looks. It's much bigger, obviously. This is this is called the social accounting metrics, which is built from the supply use tables that are taken from the SSB site or any statistical bureau of any country, obviously. And it's basically money. This will be like norske kroner or euro, whatever. It's like how much these different activities here. So first of all, it's squared. Same number of rows and columns with this, and it's symmetric. It's not symmetric, but it has the same element in row and column. Of course, not symmetric metrics, obviously. And it says how much, for example, the activities, let's say agriculture, is paid for buying commodities here. More precisely, how much, for example, agriculture has paid for buying fertilizers. So here we have different activities with different commodities, and how much has been spent. It's like an L on this wave. this other way. Money going from up to left. It starts with money. That's all we have. We start with money. This is the initial data. This money is converted into quantity and prices. Somehow. Somehow means that normally you set all the prices to 1, and you assume that the value here is all quantity. Because we just need the percentage change. We don't care about the total change. We care about the percentage change. So we can definitely assume that this value here is a quantity all at price 1. And then the price will change and the quantity will change. Okay? The product will be total here. And very often, normally, we use production functions that look like this here. This is called constant elasticity of substitution function. It's a production function. It says how much we can change the input of different commodities to have the same output. And it depends on the value of this sigma there, which is the elasticity. So the higher the elasticity is, the more we can exchange one input with another and get the same level of production. The lower the elasticity, the more we have to have a fixed mix, right? And very often, we just don't stop at one production function, but we nest it, like here. One production function will be just this. Let's say this is the amount of different inputs in terms of energy inputs to have this value here, whatever we get here. But normally we take this and we put it as nested into another production function, which puts it together with capital and labor. This is the input of capital, the input of labor that we needed with their elasticity. Every group, every subgroup has an elasticity, and it's taken from the, there are studies about the elasticities of different sectors. They are different sector by sector. So we know using something like that how much the sector is capable of behaving, of changing something with something else. The harder it will be to change something with something else, the more expensive will be a shock for the sector. We go with a shock and we say, okay, now you can't use this anymore. But if I cannot exchange it with anything else, I can't buy anything else. So what do I have to do? Maybe I can change the whole energy with more labor, because there is an exchange factor here. But labor maybe is very expensive, so I will have to spend a lot of money to have more labor to sort of make up for the missing energy. So it really depends on the sector. So the higher the values here for this elasticities, the more the sector is flexible. The more elasticity, the more the sector is good. It's not very good working. Okay. Okay. Now I'll show just a little bit how the model looks like. A very simplified version of the model, just to give a glance. And we used what's called Mathiesen approach. Mathiesen approach is, so normally you can solve these models by taking classical maximization of utility, classical minimization, mixed maximization of profits with constraints, for example, on budget. And when you have the first order condition, you put everything together, you ensure that demand and supply are equal for each good. You ask in the system, you put supply of this good equal to demand of this good. And demand comes from utility, supply comes from the production function. And at the end, you have a price that ensures that there is a equilibrium. You can do that, but something is missing if you do this. With the Mathiesen approach, you can model something like this. It's a structure, it's based on mixed complementarities. It's based on complementarity problems. Complementarity problem is, I don't know if you're familiar with that. Complementarity is when you have an equation with an inequality, which is associated to a variable, like Kershkin-Taylor conditions, if you know about them. And it's like you have this first part, which is a sort of an inequality that will be strict. It will be binding. If it is binding, then the associated variable is positive. Otherwise, if the associated variable is 0, then this inequality will not be binding. Why is it used in this case? For example, to model this problem here. Well, first of all, you want to cover all your costs. And by costs, I also mean cost of capital and cost of labor, everything. Cost of capital will be profit, basically, right? So if your sector is working fine, you're covering all the costs, which means that you have zero profit. Zero profit means that you're covering the cost of the capital. So you do have profit. You don't have extra profit, right? But if you're covering all the costs, also the cost of capital, you make zero profit. In this case, you produce zero profit. So you have an equation equals 0 binding. and the associated variable, the activity level, is positive, then you're producing. If you have a negative profit, you're not covering all the costs, then you need to have the associated variable, the activity level, at 0. Do not produce. That's the complementarity here. At the same time, you have a complementarity for supply and demand. You can have oversupply of something, then the price is 0. If there is much more supply than demand, the price is 0. Think about breathing. I mean, air is in oversupply. Luckily, we don't have to pay for that. But imagine that air was in bottles and we didn't have enough of it, then it will skyrocket its price, right? So if you oversupply something, the price is positive. If supply is equal to demand, if you oversupply that, price must be 0. You can breathe all you want, don't pay for it, right? And finally, you will have the total expenditure is equal to total income. Everything that we spend as a household, let's say, needs to be equal to all the money that we get from lending our work, lending our capital to companies, and working and owning. Okay, so that's the structure. That's the structure of the model. Now, how is it mathematically made? We have I'm not sure I should go here, and maybe I'll go on, and it just looks ugly, but it's not. We have these 3 conditions, basically. We have, I can just give a small glance. We have non-negative activity levels. I've talked about non-negative activity levels, right? I just said that if you are not gaining enough, if your 0 profit is negative, then no activity level, 0, right? Otherwise, it's a positive activity level. So we have a vector of activity levels. Either we work or not. Then we have a vector, and these activity levels are related to sectors, every sector. Then we have a vector of prices, and these prices are related to commodities. And they might be 0 if there is oversupply. Oversupply commodity, price 0. So supply equal demand, price positive. And then we have a vector of incomes. And the model looks like this ugly, basically. Not normally, the structure. This is a complementarity. 0 profit condition is negative, minus profit is negative, positive. So then this needs to be 0. This thing here that looks ugly, even uglier, it's based on something that is called Shepard's lemma and Helling's lemma. It's a result in microeconomics. Basically, if you have, and it comes from envelope theorem in mathematics. So in microeconomics, if you have an optimal profit solution and you take the derivative of the price of the output, then you will have the supply of the output. And if you have an optimal cost for something and you take the derivative over the price of an input, you will have the demand of this input. That's pretty much that. That's where it comes from, this thing. So you're taking the derivative to get the demand and the supply. Here you get the supply, here you get the initial amount, the endowment that you have already, of a particular, let's say, good, and here you have the demand. Supply larger than demand, then the price is 0, oversupply. Supply equal demand, price positive, as I said before. And then we have that the total expenditure is equal to the total income. So I'll skip directly because I don't think I have more time. Here's how these costs and profits are computed optimally. We don't care. And I believe, how much do I have? It's already over time.
Still,
I can. Okay.
5 minutes more.
Right. Then I'll go directly on the results, on what I've been run. So this was like the type of relations that we have on the model, and just I wanted to show you how bad it looks. It's not that bad. It just looks ugly. And this is the structure of a typical structure of a cost function here. So starting from this constant elasticity of substitution function, if you minimize the costs for satisfying 1 unit of output, you can end up with a closed formula for the costs, the optimal cost. That looks like that, basically. That depends on the prices of it. So basically, everything depends only on the prices here. Because the quantity, you don't care. You find the optimal quantity. You have a formula for the optimal quantity that depends on the prices, which you put back on the cost function, and you get something this ugly, but it's ugly, but it makes sense in the sense that this is the optimal cost function, starting from a constant elasticity of substitution production function. Cost larger than revenue, and then we operate. And then we don't operate. Cost equal revenue, and why the activity level of the sector is positive, as I said before. These others are the are the other supply equal demand here. So these are all the derivatives for every commodity. Okay, the derivative of costs by each commodity, the derivative of revenue, optimal revenues by each commodity, so that we have the supply and the demand of each commodity. So I'm just telling this because if you stumble upon a CGE model, you know what is for. You don't need to know it, but it's like, okay, this guy told me that they look ugly, but this is the reason. Okay, and the last one here is total budget equal to the money that we get from capital labor, the money that we get from taxes, the money that we get from different sources as households, basically. Okay. The model can be made, this model that has shown so far is normally made for what-if analysis. It's like we have an initial value that is calibrated. All these values that you saw, this data that you see here, these values, if you see any data somewhere, tell me. But Y0 is 0, all these values are calibrated from the social accounting metrics, which is the initial metrics that I've shown with all the data going from each sector to each agent. And it's used for making what-if analysis. Like you have this data initially in the social accounting metrics, then you change something, and how does the social accounting metrics change if we do this shock? In particular, if we include the tax, for example, on fossil fueled vehicles. So, and then you have a what-if. But you can also make it dynamic and try to explain how a particular pathway will change over time by including, well, the growth in population, for example, the growth on the amount of different resources. And also here, this is a formula that is used for the recursive update of capital. So basically the I here is the output of the utility function of the investors. And this output is just added to the capital from the previous year minus the depreciation. So capital previous year is depreciated plus new investments gives us the new capital that is used in the economy. So this is a typical update formula that makes the model dynamic, recursive dynamic in this case. Okay, this is an example of actually a real social accounting metrics that are built for Norway. It's not used for REMES. This is much smaller. This is just an example, but it's made with real data. And you can see, for example, how agriculture there has spent 118 billion kroner for buying agricultural products. The ag is the product here. So the first four, ag, in, serv, trans, energy, is sectors. There are 5 sectors there. And then we have products. Product of agriculture, product of industry, product of services, all bundled again. We have capital here, which is the money that's been given for repaying capital, so profits from this sector. Labor, which is money that has been given from agriculture for paying the labor, so wages. We have taxes, and that's it. So the thing is also that the sum of the column needs to be equal to the sum of the row. Yeah, this is just technicalities then. Anyway, this is how it looks like, and this is how it's read. So it starts from top and goes to the left, and it's money. Money that energy has been given to agriculture to buy agricultural products, for example. Yeah.
How often does Norway publish this type of data? How long?
Normally every year or so. Yeah. So, but there are like cases for Europe that we take from Exaiobase, for example. That is last version was from 2011. So not very good for Europe, and for Norway, I think it's yearly. Okay, some glances of what we've been doing for NTRANS with such a modeling stuff. We've been doing, and there is this output here. There is a report from NTRANS. We've been modeling social economic transition pathways, and that we have been developing as a group here, and to analyze what is the impact, in my case, what is the economic impact of these pathways. Oh, again, this is a glance. So these pathways are for, and they change depending on the level of technological change, and they change depending on how much the social and political behavior is going to change in the future. So the more we go towards this side here, the more we go, for example, for circular economy, the more the state will make laws to, for example, eat in a way that is greener, to decrease the consumption of meat, something like that, you know, if we go this way. If we go up, there is the technological change. Either we keep down, we keep as we are today. If we go up, CCS works great and that doesn't cost anything in the future. Assumption, okay? Because we are great at technology. And this is an example of a storyline that I get at the beginning. So the incremental innovation pathway is characterized by gradually known. You don't have to read that, but I start by reading those things and then just underlining some of the main parts that are useful to understand how the pathway works. Basically, this is a narrative, and you need to quantify that. Out of those points, I create for each of these 4 pathways, I take a sort of key takeaway, and for example, for an incremental innovation, we have the population increases. We have on this other thing here, social change, we have the population does not increase from 2018. It keeps staying the same level. So what is the impact of population increasing according to today's standards, day growth, or population halting? What is the difference of we got something productivity is focus on growth, focus on well-being, which up to you what it means. I model that for example, by assuming a 1% decrease in productivity in different sectors if we focus on well-being. Because we say, instead of having 8 hours of work, we have 6 hours of work for everybody. So lower production per person, you have more free time. Let's see what happens. Okay. And here is examples of how I have created those mirrors here, how I have quantified that. Like, for example, population halting, we have 2% increase yearly. If you look at radical transformative, what does it mean productivity? Focus on well-being and industry 5.0. They were things written there, like, you know, like these people writing things. And okay, I know that there is going to be an improvement of a decrease in productivity. So I assume 1% yearly decrease in productivity, but also this industry 5.0 doesn't mean anything. I mean, just okay, let's make a quantification of that just for the sake of analyzing something. And I assumed, for example, an increase of 1% of productivity, of total factor productivity, only for industry, and see what happens.
Sorry, is it for Europe or for
this for Norway? Norway.
Okay.
So only Norway. Okay, so after some of these, for example, this 19% yearly decrease in extraction is taken from official, reports. Some of them are like guesswork. And yeah, this is how it looks like. For example, the change in GDP in the reference. I also make a reference scenario based on the perspective melding, the economic message from the government. And this is here. This is services, the yellow, and this is industry, the orange one. So mostly it's industry and services. And this is oil and gas, this dark blue or almost black thing. In different scenarios, so here it's how the GDP will change in different scenarios. So we have, for example, scenario, the reference scenario is the one, the blue on top that goes up. But what happens if we, for example, the population stops increasing, if we have 1% decrease in the usage, in productivity in industry, if we stop extracting oil and gas, what happens? So we have different, like Soch and Rad here are the cases where we stop growing, basically, and we stop extracting. Radical transformative goes a little bit better because we have this industry 5.0, which I have transformed into 1% increase in productivity in industry only. And we can also use green hydrogen. So here we have different levels of GDP depending on how big the shocks were. I'm not going to explain everything in exact minutes. And these are other scenarios and how they look like. Here you can see how oil and gas change. Oil and gas is shrinking in basically these two scenarios that I can't read anymore. In Soch and Rad, and Ink and Tech, they keep having, in Ink we keep having global oil and gas, so we keep selling it. So it doesn't decrease, doesn't increase either, but it doesn't decrease at least. But in Tech it does decrease. And in the others, it's even worse. It decreases a lot. We are phasing it out. Also, we have impacts on other sectors. And just a very small thing without explaining it because no time. This is what happens to the activity level, or sorry, the value added for industry in the different cases. In these two cases here, it goes real bad. So it's social change and radical transformative is called. Here we have more circular economy, which I have translated into people stops buying things and uses more services. People fixes the phone rather than buying a new one, and so on and so forth. What happens if we move towards services? This is industry, so not good for industry in this case. In fact, it goes down. It goes better for services, obviously. Still, see, here it's bad for many things. The economy is bad because we are not growing anymore. The population is not growing. The thing is going down. The productivity is going down. We have moreover, we have circular economy kicking in. So industry goes real bad, but for services it's a little bit better because of circular economy. More services, less industry. Here are some other examples of, for example, what happens to fuels, how they change over time in the different under the different scenarios, and how the prices change. Here, the price tends to stay the same all the time, even if the demand goes down, because there are some sectors at the end that keep using some of it. But we are phasing them out. So no supply anymore, still some demand, residual demand. For this residual demand, the price might skyrocket. Well, skyrocket, increase. And this is for electricity, a similar analysis. What happens, because we can analyze a lot of commodities and more. We have many more analyses that will come from this report, if anybody's interested. And run social technical pathways and scenario analysis. And I believe that's it.